In 1955, after the death of his closest friend, Albert Einstein wrote these words. For us, believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. To understand what Einstein meant, we first have to answer a deceptively simple question. When does present actually happen? Look around you. You think you're seeing the present. You're not. You've never actually seen the present. Not once. Everything you've ever seen was already in the past. But how can something right in front of your eyes already belong to the past? It all comes down to one simple fact. Our eyes don't see objects, they see light. Every object around you is constantly sending out light. When some of that light reaches your eyes, your brain finally recognizes what's there. You'll never see the object itself, only the information it sends as light. And that light travels at nearly 300,000 kilometers every second. Fast, but not instant, which means by the time light reaches your eyes, what you're seeing has already happened. Even the light from your phone screen takes time to reach your eyes, about half a nanosecond. So by the time you see this video, it's already in the past. Now imagine much greater distances. Light from the moon takes about 1.3 seconds to reach Earth. So every time you look at the moon, you're seeing it as it was 1.3 seconds ago. Light from the sun takes about 8 minutes. If the sun vanished this instant, Earth wouldn't know for another 8 minutes. And then there's the Andromeda galaxy. Its light travels for more than 2.5 million years before reaching Earth, which means you're seeing Andromeda as it was 2.5 million years ago. The farther away something is, the farther back in time you're looking. So here's the real question. If every event reaches us only after light carries its message, how can we ever know when it actually happened? Here's the trick. The time on your watch isn't the time the event happened. It's the time the information reached you. To find the real time of the event, you subtract the light's travel time. Time of event equals time you saw it minus light travel time. Now imagine you're standing on a railway platform. Your friend is sitting exactly in the middle of a moving train. As the train passes you, two lightning bolts strike. One hits the track at the front of the train, the other at the back. And you happen to be standing exactly halfway between them. Each lightning strike is 4 light seconds away from you. A light second is simply the distance light travels in 1 second. So each flash needs 4 seconds to reach your eyes. And that's exactly what happens. Both flashes arrive at 12 hours, 0 minutes, 4 seconds. Now apply the same rule. Event time equals observation time minus light travel time. 12 hours, 0 minutes, 4 seconds minus 4 seconds equals 12 o'clock for both lightning bolts, which means they struck at exactly the same moment, simultaneous. Now watch your friend. He's still sitting exactly in the middle of his train, but the train isn't standing still. It's racing forward at 60% of the speed of light, toward the front flash, away from the rear one. So from where you're standing, you can predict what happens. The front flash reaches him after 2.5 seconds. The rear flash has to chase him. It catches up after 10 seconds. Now look carefully at those two numbers. 2.5 seconds, 10 seconds. Whose clock measured them? Yours. You measured them standing on the platform, watching your friend. But your friend has his own clock. And in the last video, we uncovered something remarkable. Moving clocks run slow. We measure that slowdown using a number called gamma. At 60% of the speed of light, gamma is exactly 1.25, which means to find the time on your friend's clock, you simply divide by gamma. So on your friend's watch, 2.5 seconds becomes 2, 10 seconds becomes 8, which means the front flash arrives at 12 hours 2 seconds, the rear flash at 12 hours 8 seconds, 6 seconds apart. Now imagine your friend's point of view. He's sitting exactly in the middle of the train. The front flash reaches him at 12 minutes and 2 seconds. The rear flash at 12 minutes and 8 seconds. 6 seconds apart. But remember one other thing we learned in the previous video. Light always travels at the same speed. It doesn't matter whether you're moving toward it or away from it. The answer never changes. The speed of light. So from your friend's point of view, the light from the front and the light from the back both traveled at exactly the same speed. He's sitting exactly in the middle of his train. Yet one flash reaches him 6 seconds before the other. There is only one possible conclusion. The lightning bolts did not strike together. The front bolt struck first. The rear bolt struck later. And from his point of view, he is absolutely right. You both watched the same train, the same lightning. You both trusted the speed of light. You both followed the exact same logic. Neither of you made a mistake. And yet, you couldn't agree on when it happened, which means there is no single universal now. There is your present and your friend's present. Neither is more real than the other. Einstein was right. For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. That is the relativity of simultaneity.